Herzog, President of the State of Israel, Orit Farkas-Cohen, Minister of Innovation, Science and Technology, Her Excellency Sarah bint Youssef El Amiri, the UAE Minister of State for Advanced Technology and Chairwoman of the UAE Space Agency, Major General Professor Yitzhak Ben Israel, Chairman of the Israel Space Agency, Brigadier General Uri Oron, Director General, Israel Space Agency, distinguished heads of state agencies, dear friends. Space exploration is often seen as the science of gazing outward towards the stars, but in truth, the technologies that allow us to explore distant galaxies are critical in helping us understand the Earth beneath our feet. And the tools we are developing to study other planets can help us save our own. I am proud that the current Israeli government is, for the very first time, taking climate change seriously. We have set a net zero emission goal by 2050, passed a landmark decision on transition to a low carbon economy, and set new policies in areas of transportation and industry to clean energy and green building. And this is just the beginning. We are now formulating comprehensive climate legislation, developing a new system of carbon pricing, and advancing the transition to a circular economy. In short, we are not only finally aligning ourselves with the standards of the world's most developed nations, but we are positioning ourselves to play a leadership role in the global climate transformation, particularly through cutting-edge climate innovation. Yet, as COP26 made clear, despite the growing international understanding of the climate crisis, we still have many obstacles to overcome if we hope to avoid a climate disaster. There are still significant gaps in our ability to monitor, measure, and analyze the global data in climate change, to set clear benchmarks and realistic goals based on scientific criteria, and develop solutions that are effective, sustainable, and scalable. Successfully mitigating climate change will require utilizing every field of study, science, and human endeavor. Space exploration, which pushes the very boundaries of human knowledge and capabilities, can play a key role in this effort. To be honest, we are only just beginning to understand the true potential of technologies such as advanced satellites, sophisticated imaging, and predictive analytics based on data gathered from across the planet to assist us in mapping the current state of natural areas, measuring changes in the atmosphere and oceans, tracking and combating severe weather events like forest fires, devising holistic solutions to challenges like urban heat islands, and even improving the health of forests and increasing agricultural production. That is why I am advancing unprecedented cooperation between the Environmental Protection Ministry and the Israel Space Agency. One key project carried out in the partnership with our friends in the Italian Space Agency is the Shalom satellite program. Together, we are exploring ways to maximize this program's contribution to our collective effort to understanding and mitigating climate change. We are also actively exploring cooperation with other space and satellite programs, including NASA. As we expand our connections with new and old regional partners, especially the UAE, and look ahead to the next UN climate conference in Egypt and in the Emirates, I believe that the nexus of climate and space will play an increasingly important role in regional scientific operations. Friends, we are at the start of a very exciting journey toward realizing the potential of integrating space exploration and climate action. This journey will help us to preserve our own planet and explore new ones. I look forward to learning from your insights and to finding new ways to work together. Thank you very much.
Space technologies have led to a number of inventions that benefit the environment and save energy. Satellite-based systems are reducing vehicle carbon dioxide emissions. Remote sensing technology is making wind turbines more efficient, and information from weather satellites is helping solar cells to produce more energy. During our conversation, we will address the implementation of commercial applications the opportunities for international cooperation, and thoughts about the future. Our panelists today are addressing these challenges and designing the solutions to enable mitigating climate change challenges today and for years to come. I'm honored to present the panelists. Dr. Karen Germain is the director of NASA's Earth Science Division. She provides executive leadership in the overall guidance, strategy, and budget for NASA's Earth Science program. This includes designing new instruments, satellites, and systems to collect information and freely distributing the most complete and precise data possible about the entire Earth system. Professor Eyal is a full professor at Tel Aviv University. Currently, he is serving as the head of the remote sensing laboratory within this department. He has more than 28 years experience in Earth remote sensing, with special emphasis on hyperspectral remote sensing technology for environmental monitoring. He is chairing the IEEE ESA working group to establish standards and protocol for soil spectroscopy and the Glossaland Spec working group on behalf of FAO UN that aims at sharing Earth observation spectral-based information for global utilization. Dr. Francesco Longo is the head of the Earth Observation Division at ASI. He is in charge of definition, realization, operation, and data exploitation for the Earth observation missions of the Italian Space Agency. Dr. Frederic Bretar is the head of Space Climate Observatory at CNES. He is in charge of building the SCO initiative, seeking the commitment of international partners, and managing the SCO France implementation that is federating the French community, making emerge projects, managing the SCO French project portfolio, and nourish the global communication. Mr. Goffer is the co-founder and chief strategy officer of Tomorrow.io. As CSO, Re'i oversees the company's space portfolio and its government business unit. Re'i served for 10 years in the Israeli Air Force as an F-16 navigator and R&D program manager. He holds an MBA in economics from Ben-Gurion University, an MBA from MIT Sloan School of Management, and an MBA from Harvard Kennedy School of Government. Please join me in welcoming our panelists. Let's start with a short presentation of your organization's contribution to tackle climate change. Please share some examples from your work for such use cases. Karen, the floor is yours.
Thank you so much, Adi. It's wonderful to be with you all. NASA is the US space agency that has the end-to-end mission for understanding our Earth system, including climate change. So we start with investing in technology, in building flight systems, in funding the fundamental research and the modeling that extracts understanding from those observations, and then moving that, that scientific understanding into action through our applied sciences program. In fact, NASA observations and research underpin a lot of what we understand today about the changing climate and allowing us to predict how it may continue to change in the future. A couple of examples, though, now to be forward-looking. So that's a look back, but to be forward-looking, we are developing this decade the Earth System Observatory. This will be our next generation system to answer the most urgent questions identified by our National Academy of Science, including those associated with climate change. The Earth System Observatory will have 5 core missions that will be treated as a single observatory, looking at the atmosphere, the surface of the Earth, as well as the subsurface, to understand how that is all working as a system and responding to the changing climate. On the data side, we're moving forward with our open source science initiative, and we think this is the real key to unlocking action on climate change. It's an effort to fully open not just our finished science, but also the research while it is happening. So it's based on the principles that wider participation will accelerate our scientific discovery and the uptake of science to support decision making. So those are two of our ongoing major initiatives that we think will have the potential to substantially contribute to climate change.
This is great. Francesco, let's hear about ASI.
Thank you very much. When it comes to climate, space is vital because there are events or data sets that we cannot acquire in other ways. Let me give you a couple of examples. If you want to see how the ice is changing over the poles, which is a fundamental part of weather system, you can explore it from space to the Cosmos Climate Constellation, the CERNIX band of the Italian Space Agency. ASI is contributing to tackle climate change with the data obtained by this SAR constellation, with specific acquisition plan activated from early 2014 and oriented toward the monitoring and study of polar caps elements as ice sheets, permafrost, snow, and floating ice. The Italian Space Agency is also involved in the Polar Space Task Group. This international working group facilitates the acquisition and distribution of satellites dataset and contributes to developing specific products for cryosphere, polar, and high mountain scientific research and application. In this context, ASI is acquiring massive data that populates a dedicated mission archive over Arctic, Antarctic, and Greenland glaciers. These CSK data, the Cosmos Climate Constellation, are included in the mission catalog and available for scientific international Earth observation community in the context of the Italian Space Agency Open Call Initiative to guarantee access to the international scientific community, considering the synergies with other EO Earth observation missions and the complementarity of other remote sensing data. To achieve this objective related to climate monitoring, we have a commitment to fly SAR mission regularly, so to provide enough continuity to the observations. A mission lasting 5 years and not replaced by another mission could properly support, in fact, climate studies. We need 20, 30, 40 years of data. For the reason, the latest update of this call also included data acquired by the second generation of the Cosmos Climate Constellation, whose second satellite will be launched this January, the 27th, from Cape Canaveral. ASI developed a similar approach also for L-band and hyperspectral mission like PRISMA, L-band SAR. Hyperspectral sensing is a key Earth observation technology able to offer an unprecedented contribution to observation of the Earth from space, to study the effect of climate change, such as environmental degradation, the correlated desertification, and wildfire risk assessment. In this field, my agency is currently moving toward the PRISMA second generation to guarantee the observational continuity, which is very important for climate understanding process. Our commitments are not limited to building the space infrastructure. We have a lot of data. We have terabytes of data that we want to transform in information useful to detect environmental changes on Earth. And we have to be far more active in making this data available to scientists in order to quantify climate-related changes. These are the essential climate variables that include atmospheric, telestial, ocean observation, and provide a clear message, trends, and historical on future climate change. Concluding, this is the success we must achieve with our work.
That's great, and good luck on your
Thank
launch soon. Frederic, please.
Yeah, hello. So actually the CNES, the French Space Agency, is involved in many Earth observations programs and is doing a lot for climate change. But I will focus on a quite a specific program, the Space for Climate Observatory. This is actually a 2-year-old program. So this Space Climate Observatory is an international alliance of space agencies and UN bodies like UNOSA, UNDP, UNEP, and with local implementation. There is an international alliance and then local implementation like the SCO France in Mexico, in Russia, in China. Okay. Between all these space agencies, we found, of course, France, China, Russia, Israel, Italy as well, and the ESA, and soon maybe the NASA. So this alliance was born in 2019, following an international summit led by the French President Macron, the One Planet Summit. And actually the CNES has been designated to implement it. So this alliance aims to provide operational tools and studies to help decision makers to adapt to climate change, especially at local scales, using satellite Earth-based observation tools in combination with field data and models. So why the involvement of all these space agencies? Because this initiative is unique at international scale. It allows space agencies to enhance the value of satellite data as close as possible to the actors in charge of adapting the territories to the impacts of climate change. The SCO is actually an algorithmic accelerator that aims to enhance the scientific community's output and eventually develop customized climate services for clearly identified end users. There are many topics in these different projects, like the land use, biodiversity, carbon monitoring, extreme meteo events, energy, natural disaster response, agriculture, health, water management, etc., etc. Everything is very well documented on the website of the spaceclimateobservatory.org.
Great, thank you. Eyal?
Thank you, Adi, for giving me the opportunity to be part of this panel and to all the panelists. In the Tel Aviv University Remote Sensing Laboratory, we are excelling hyperspectral remote sensing of the environment from all domains, from indoor, field, low and high altitude airborne sensors, as well as from orbit. We're exploiting the hyperspectral technology to study and develop applications that other sensors cannot yet provide, as for their lower spectral resolutions. Well, some examples that we are doing: soil degradation based on fire events, mineralogy of dust in the atmosphere, as well as soil forming dust, drought indicators, surface change detection during the acidification processes, and monitoring the water infiltration rate to the soil profile based on climate change issues, such as fire events. Recently, we moved into the hyperspectral remote sensing in the thermal region. And this is actually the region that will tackle climate change in much more precise way and will add to the other spectral regions that we are working today. And to that end, we are investigating the best combination of spectral features that should be implemented in the new forthcoming thermal infrared orbital sensors. Last but not least, I would like to mention and to highlight that in Tel Aviv University, we are building CubeSats. And the next CubeSat will be to mount hyperspectral, very light hyperspectral sensor in the CubeSat and send it to orbit for tackling a couple of environmental issues. Thank you.
Thank you, Eyal. Ray?
Yes, hello, and thank you for having me. So I'm Goffer, I'm one of the co-founders of Tomorrow.io. What Tomorrow does, we are a weather intelligence platform. We're a private company headquartered in the US in Boston, and we're building the world's first weather intelligence platform that is fully vertically integrated, all the way from observations to forecasting models to the products and intelligence on top of it. We are a team of about 200 people. We've raised $200 million in venture capital, and we serve hundreds of enterprise customers, consumers, and government agencies, including NASA, NOAA, and the United States Air Force. Specifically to the topic of this conversation, Tomorrow.io is developing the world's first constellation of commercial weather radars. So essentially, we're building a constellation of small satellites, about 100 kilogram in size, that will carry a miniaturized radar instrument that is focused on measuring atmospheric parameters, specifically precipitation. Precipitation measurement. Precipitation is actually ranked number one out of 152 different geophysical parameters in terms of importance by NASA and a group of partner agencies that we still lack observations on. It is extremely difficult to measure precipitation given the high temporal and spatial variability of it. Think how frequently rain starts and stops, and it can rain on one side of the street but not rain on the other. And right now, what we have are few very limited tools globally. We have rain gauges, the dripping buckets. If we take all the rain gauges in the globe and put them together, we would cover something like the size of a football field. So that's really undersampled. And there is rarely any of them in places like Africa, in places like Latin America and others, and of course over the oceans. The second method we have is using radars, ground-based radars, which are great, but are extremely expensive and complicated to operate. And so today, even though this technology is about 70 years old, we still only have radars on the ground in maybe 5% of the world. So United States, Europe, Japan, and a couple of other places, but 5 billion people on the planet live outside of radar coverage. And obviously radars, terrestrial radars, can't cover the oceans. And so storms coming from the ocean to the land cannot be monitored with this technology. The last option is from space. And NASA has an incredible heritage in building, developing, flying spaceborne radars, precipitation radars. But these instruments are billion-dollar spacecraft in low Earth orbit, very expensive, very complicated to operate and build. And so we only have a handful of them. In fact, today we only have one of them on orbit. With one satellite in low Earth orbit, you can achieve revisit rates of every 3 days, more or less, which is useful for science applications. We get an overpass on a storm maybe once or twice in its life cycle. But it's completely useless for operational forecasting because our forecasting models need to be updated every hour or every few hours. And so to achieve high revisit rates with global coverage, we need to fundamentally change the architecture of these instruments such that they can be mounted on much smaller satellites, such that each satellite is much cheaper and we can deploy many of them to achieve global coverage and high revisit rates. That was considered a dream, and NASA actually had an attempt to miniaturize it. It's called RainCube. It's a small CubeSat that proved some of the pieces, but it's still not a scalable architecture. It does not scan, so it has a very low footprint. And we basically are developing and launching a constellation of wide swath, so very wide coverage instrument that combined will give us high revisit rates. And again, quoting NASA on this topic, if you did that, you would revolutionize climate science and weather forecasting. So this is what we're up to. We're launching the first 2 satellites late this year in 2022. And we're planning a full constellation of roughly 30 satellites on orbit by the end of 2024.
Sounds terrific, and good luck with that. So thank you, everyone. Now that we all know each other briefly, we can continue to specific questions focused on commercial aspects. In particular, we will try to understand how the commercial entities blend in the global endeavors to mitigate the climate change challenges. Frederic, let's start with you. What is the involvement of commercial entities and the service to commercial and private end users?
Yeah, thank you, Eddie. Actually, I will again take the focus of the Space Climate Observatory. Actually, the SCO was built to provide an answer to the complexity of transferring scientific methodologies to society and to integrate the wealth of information extracted from Earth observation satellites into systems. And these systems are designed for local decision makers. For a project to be accredited as a SCO project, it must be supported by a consortium bringing together scientists, at least one end user, very well identified end users, and one service operator. And this service operator is often very often a private company, but it's not always the case. And today, our portfolio of 36 projects for the SCO, the French implementation of the SCO. There are approximately 30 companies involved in the different projects. Different size of company. Some of them are dedicated to graphical user interface, some of them for data analysis, some of them specialize in the analysis of space data.
Sounds great. Ray, how does a software company decide to embark on a journey to develop its own satellite? Why not buy something ready?
Yeah, good question. It wasn't an easy decision. When we started, we basically said, well, there is a huge gap here, and we've tried all sorts of other ways, by the way, to solve this gap from the ground and doing all sorts of other kind of technological attempts. But at some point, we realized the only way to solve it is from space. And then we started looking at who's doing similar stuff in space and seeing if somebody's already doing that or can do it with a small deviation from where they are. And what we learned is that there was nobody that got even close to that. There is the government, and I mentioned the amazing NASA efforts, but when we spoke with the group at JPL, they were like, well, this is not anywhere, maybe 10 years away. So we said, solution is not going to come from there. And we looked at the private companies, and yes, there are a few private companies doing stuff on weather, and also a few private companies doing stuff in SAR, in radar from space. But comparing SAR to a precipitation radar is like comparing a bicycle to a high-speed train. It's a very different application. We're working at much higher frequency. We need to scan wide swaths of land. It's almost, think of like driving a race car and having to count the pebbles of the road track while you're driving. So it's a very, very different technology. And none of the technologies or solutions we saw online when we started was getting anywhere near enabling that. So we said, well, we need to do it ourselves. That's the only way.
Okay, Francesco, extreme events are happening more often and becoming more intense. What role plays Earth observation infrastructures in detecting event warning signals, emergency assistance, and post-impact assessment?
Thank you, Eyal. There is a growing evidence that extreme events are increasingly impacting people and our planet, and more frequent, intense extreme weather and climate-related events, as well as changes in average climate condition, are expected to continue to damage infrastructure, ecosystem, and social system that provide essential benefits to communities. Earth observation is able to contribute by providing data for services and applications addressing the different aspects of all kinds of events, extreme events: mitigation, preparedness, response, and recovery steps. In particular, mitigation refers to action to be taken before an event, reducing the overall risk and the impacts of extreme events. In this phase, Earth observation satellites data could contribute to vulnerability assessment and provide indication on maintaining infrastructure. For example, the possibility of evidence dangerous landslide through expand synthetic aperture radar, or in conjunction with Eyal and C-band. Preparedness, and this is very important because it is done before an event or a disaster. Earth observation satellite data integrated with the in situ measurement could be useful to develop early warning system. For example, the instrument on the European Meteosat third generation satellite will track the full life cycle of storm. And this is a national program, the synthetic aperture radar based on geosynchronous satellite. And they will improve the prediction capability for intense storm and their related impacts, such as flood and landslide, that cannot be monitored by LEO satellites to the low revisit time. The response is the activities that are done immediately after the event or the disaster have occurred, saving human life and support search and rescue teams on ground. And for this step is very important, taking advantage of optical and SAR VHR in orbit. Finally, recovery phase include the post-disaster action. An example is a recovery mapping based on satellite data that is useful to monitor all recovery operation. Concluding, our planet is talking to us through Earth observation system, and we can clearly listen to it through Earth observation system.
Thank you for that. Eyal, you talked about how hyperspectral technology from space. Tell me, how can it foster commercial remote sensing-based applications?
Well, this is a good question I've been asked quite often. We have to remember that the hyperspectral technology is not actually dedicated for killer application, but it is a killer technology. It's providing high spectral resolution to remote quantitatively the atmosphere, lithosphere, biosphere, cryosphere, and pedosphere. As other resolutions, spectral resolution already, spatial resolution are already achieved by both federal and commercial satellite entities. The adding information with the spectral high spectral resolution the hyperspectral remote sensing provide may be a game changer to study the climate change issues in more quantitative way. As this technology is rapidly entering into the Earth observation topic by ESA, DLR, NASA, JAXA, ASI, and hopefully by ESA as well, it is only expected that the commercial sectors will enter soon the game. Well, it means that commercial entities will develop and launch hyperspectral remote sensing sensors that will be harmonized with other sensors to provide the best answer on climate change phenomena in all of the global sphere. Example for that I can just have in mind is, for instance, PlanetScope initiative that is planning to have the CO2 sensor in orbit, which is based on the hyperspectral legacy of JPL. Other pillar of hyperspectral technology is to introducing the technology to companies that are providing applications in agriculture, disaster monitoring, forecast fire potential issues in forest, environmental, and more. The hyperspectral remote sensing is not only a sensor with reliable quality, but also a technology that needs sophisticated processing chain using AI and machine learning and all what we have from data science today. The initiatives that will provide high spectral, spatial, and temporal resolution, along with providing tailor-made services to many end users, will lead the Earth observation business with a significant revenue. ASI, for example, and ESA are targeting this direction by the new Shalom initiative.
Okay, you talked about a few things about the Shalom project, of course, of ESA and ASI. We talked about data fusion and about machine learning and the need to have automatic tools. This is, of course, very important when you talk about hyperspectral technology. Karen, is NASA involved in supporting the development of climate change monitoring capabilities in private industry? And if so, how?
Yes, thanks for the question. NASA's history of working with private industry is it's a long history, and it's pretty vibrant. I'll talk about 5 different ways that we collaborate across public-private the boundaries. So, of course, the first is the most obvious. The private sector is deeply involved in instrument, spacecraft, and launch, and the innovations that enable them for all of our NASA missions. And so that's sort of the longest standing way that we collaborate with private industry. Of course, on the other end of the value chain, our data enable the industry that exploits the Earth observation data and turns that into services. And some of those have been mentioned already today. And we think that's a great use of our data by the private sector. We even when we competitively select missions, we also there expect to have significant private industry involvement. So for example, we have the upcoming Earth Explorers missions that will be competitively selected. Many of those contribute directly to climate change understanding. And we certainly expect that the private sector will be bidding for those missions as well. We focus a lot on transitioning technology out into private industry. A recent example of that is the Carbon Mapper program, where we're taking NASA developed technology and transitioning it out for broad commercial application. And then finally, the fifth way is, of course, when private companies field their own Earth observing systems. And we've heard about some of that today. We can and do often use their data to augment our own research. And we have a whole commercial data program set up around buying private industry data to support Earth science research. So there are a lot of ways that we I would say collaborate and are mutually supportive.
Thank you. Climate change commercial applications, as well as governmental efforts, can be joined together to mitigate these complex challenges. Rei, this is one for you. If your satellites are so enabling, why hasn't NOAA, NASA, or other private company already built someone like that?
Great question. It's not that trivial, and I think there are a couple of elements to it. One is, NASA tends to not do the same thing twice, right? So if they've done, one precipitation radar, they'll move on to the next thing. Their mission is science, right? So I spoke about precipitation radars, the difference between that for science and operational meteorology. NASA does not run forecasting model, nor does its mission. It's to support forecasting models. And then you have the other agencies, the weather agencies, NOAA or UK Met or any of these guys. And here it's really just a matter of pace of innovation between government and private entities. And I think you can see it across the board. If we stay within the space industry, of course, taking some high comparison, but why did nobody build reusable rockets before, right? If it's so enabling, which it is, why didn't the government do it before Elon Musk did it, right? So private market has a very different tolerance for risk and approach to R&D that is often not a good fit for government-funded programs. And this is just another case of it. We saw a very strong need, well-defined, with really big market opportunity behind it. High risk to get there, but as soon as we convinced ourselves that we can overcome this risk and mitigate it, we were able to execute on it. It's just a very different cycle and mentality than government innovation.
Thank you. Eyal, talking about international collaboration, what is the essence of hyperspectral technology in that matter?
Well, international collaboration between space agencies is a key factor to combat the climatic change issues. This implies to any Earth observation sensor in general and particularly valid for the hyperspectral technology from space. For example, NASA and ESA are collaborating together today with developing orbital hyperspectral sensor separately, but they are collaborating in order to harmonize information and know-how. They're also conducting, for example, airborne campaign with many global users to prepare the community for the forthcoming hyperspectral remote sensing era from space. So sharing know-how and facilities is also a significant factor between nations, as it's such collaboration is needed to complete and not to replicate the data and the products. synchronizing orbital sensor to increase the temporal resolution is one of the significant examples how international collaboration is important. Another important issue is the combination of other information derived from other sensors, such as the forthcoming CO2M of ESA, LSTM of ESA, SBG of NASA, along with existing sensors such as EcoStress, Sentinel series, and other high spatial resolution sensors. Another issue that need international collaboration, which is very important, is actually the debris in space. We will need to improve and generate regulation for that. Otherwise, the space, as the Earth, will be contaminated with a lot of debris. Collaboration between space agency and private sectors such as PlanetScope and NASA is very important too. Climate change phenomena is better observed with many sensors are harmonized. It would be just fair to mention and appreciate NASA Open Science, as Karen mentioned before. This should be adopted by other agencies to follow this direction. I would like to give you more example about international collaboration. There is a group, GEO, is the group on Earth observation, and they have also GEOS, Global Earth Observation System of Systems, that have more than 100 nations as members. They both increasing and providing access to diverse information for a broad range of users in both public and private sectors. This is a very good example how collaboration can be done in global wide. Another collaboration pillar that is foreseen in the harmonization of ground truth information. Vicarious calibration activity over the north and southern hemisphere should be managed in a more practical international way. This is my opinion. The new concept actually of citizen science may be also a good idea how international collaboration can foster the connection between the citizen and space technology, and especially to the climate change issues.
Thank you for that. And here's a question to Karen, Francesco, and Frederic. The issue we are dealing today is a mission across countries, across organizations, and across agendas for the benefit of all humanity on Earth. And we have you as representatives from space agencies operating, of course, in this field, as you mentioned before. And what is the power of international cooperation in this matter? Karen.
It's a great, and I would say very important question. International collaboration is absolutely essential to what we do, both historically, but also, again, as we look forward to our next generation systems. And the international collaboration allows us to do more than the sum of what each nation would be able to do individually. Let me give you an example. The Surface Water and Ocean Topography Mission, or SWOT mission, just is a great example. This is a collaboration between NASA and CNES, and we're jointly developing this mission with contributions from the UK Space Agency and the Canadian Space Agency. So these agencies coming together are going to do something that we've never been able to do before. SWOT will provide the very first comprehensive view of Earth's freshwater bodies from space. It will allow scientists to determine changing volumes of fresh water across the globe at an unprecedented resolution. And specifically, hydrologists will use the data to calculate the rates of water gained or lost in lakes and reservoirs and wetlands, as well as measure the discharge variations in rivers. These measurements are key to understanding surface water availability and providing important freshwater information for hazard response management, irrigation management, reservoir management, navigation, among other things. SWOT will also revolutionize ocean physics and sea level and climate science by detecting ocean features with 10 times more better resolution and higher accuracy than our current technologies. These small but very energetic ocean features like fronts and eddies are key contributors to Earth's fundamental cycles of energy, heat, fresh water, moisture, and carbon. So observing and understanding these never before seen features globally will unveil new physics of Earth system interactions and improve predictive capabilities of Earth system models. So, this is just a great single example of what international collaboration can enable. And it is far more than the sum of the parts.
Thank you. That's great. Francesco?
Totally agree with the current words. The international cooperation is fundamental to have a rapid and intense response for climate change. An example is the mass change and geoscience international constellation MAGIC, a very important cooperation between NASA and ESA and all the sister countries of ESA, among Italy also. But the need for accurate and precise data on the planet's current state has never been more urgent, and the international cooperation is at the heart of these activities. In this context, my agency is deeply involved in several initiatives with the Israeli Space Agency to develop a challenging hyperspectral mission named Shalom, and with NASA for the designated observable in the thermal infrared, fundamental for evapotranspiration, ability to understand if ground is stressed, and we have to irrigate without wasting resources. With the Argentinian Space Agency, with CONAE, for developing an integrated L and X-band submission, and as part of the European Space Agency to develop Copernicus or Earth Explorer. And this cooperation between countries simulate connection, coordination among missions. For example, the thermal infrared between NASA and ASI with the ESA mission LSTM or the Franco-Indian Trishna mission. The goal of this cooperation is to take part in a global space program and mission to build a better understanding of our planet, and as it can extend to reach resolution and richness needed to monitor Earth climate sufficiently. The list of activities in cooperation is anyhow far longer. However, I do hope that this gives a real test of the wide-ranging and depth of the Space Agency climate-focused activities, all of which, I reiterate, are dependent on international collaboration and cooperation.
Thank you, Francesco. Frederic?
Yeah. Adapting to climate change is above all an international issue. We have already mentioned it, but I will not come back on this point. There are numerous international organizations, formal or informal organizations dedicated to this topic, like of course, UNFCCC, in our field, the CEOs, the GECOS, GEO, we have mentioned GEO also that is working on these issues, and of course, the concrete collaboration on satellite developments, like SWOT mentioned by Karen, microcarb also, or Trisna that Francesco mentioned as well. And actually, of course, one of the pillars of the SCO is international collaboration. There are today 36 SCO members, and a new charter will be signed by June 2022 to renew the commitment in the initiative. And in the SCO at international level, we are sharing experience. We build framework to improve capacity building initiatives toward the less advanced countries, as well as dialogues between big and small space agencies. So we have members like the Gabon, Ethiopia, we have already mentioned Russia, France, etc., Slovakia as well, on Malta. So there is a difference, and it's a place where all these agencies can talk. All outputs of scope projects are designed to be expandable to other experimental areas, at the initial site. And the most important is for our international partner to know these concrete solutions are existing and could be possibly used at home for their own problems related to precipitation, biodiversity, etc., etc.
Thank you for that. Actually, we are almost done. And I have one last question for the whole panel. It goes like that. The United Nations SDG 13 urges to take action to combat climate change and its impacts. We talked about the importance of tackling this issue in the framework of global ecosystem. What steps need to be taken so within the 5 to 10 years from now, we see a significant improvement? Karen, let's start with you.
Oh, terrific. Thank you. So there's no doubt that we face a serious challenge with climate change. But I think it's important to keep in mind that there is an enormous range between the best and the worst outcomes. It's millions of individual decisions contributed to the current trends. And it is millions of different individual decisions that will enable communities around the globe to mitigate and adapt to climate change. But this only happens if people take action, and people only take action if they understand what is happening. So the insight and information from the Earth observation community, both public and private, can help catalyze this response. So I'll end where I began. We must press ahead in our observations and predictive capability to create the best, most actionable information. And we must do it in a way that inspires trust. So the key for us is to double down on collaboration in deploying these capabilities, encourage all in our enterprise to embrace open science, to both accelerate the discovery and the uptake of that information to inform decisions, and frankly, also to tell our stories so that others are inspired to action. Thank you.
Thank you. Francesco?
Thank you, Adi. It's very important because what is unique about remote sensing of the Earth is that it provides us a holistic view of the whole Earth system, allowing us to understand the changes that are taking place. Without observation, which is the first step of any scientific process, we cannot understand the causes and consequences of these changes. So we have to accelerate the transformation of space data to valuable information, allowing the development of what-if simulation to support decision-making and monitor how well climate change adaptation and mitigation strategy are working. We have to stress our government agenda on supporting Earth observation measurement. There is no evidence-based information to measure, monitor, and guide global and local initiatives without Earth observation. But the most important elements that we must invest are young and education. The two key elements to addressing climate change, helping young to develop a deep interest for the Earth, bringing them closer to its knowledge, stimulating and educating them in Earth science. Young people can be taught the impact of global warming and learn how to adapt to climate change. Education empowers all people, but especially motivates the young to take action on climate change and realize that it's not about saving the planet, it's about saving ourselves.
That's terrific. Frederic?
So actually, space agencies are doing a lot to take actions, and we need to mobilize end users, decision makers to fill the gap between science and the very up-to-date science, most advanced algorithm, etc., to decision maker, and to make them know the full power of satellite informations. Actually, the computing power available to anybody able to digest all this amount of satellite data and above has never been so high, and it has to be also available for countries where climate change consequences will be actually much more terrific than in Europe or in very advanced countries, for instance. And that's what we think could be the right way for the school, for instance, try to share and to improve the capacity building to be customized to all these very advanced science and data.
Thank you. Eyal?
Thank you. I totally agree with Francesco about education and about also Earth observation being the stethoscope of the Earth. So I really think that we need to foster education relating to both environmental and space science, and to work hard for the connection between them. Also, I think we will have to see that space agencies and countries, federations such as the EC will really follow their plans while minimizing heavy bureaucracy problem and solving budget constraints that arose by unforeseen cases. You know, they put money for some mission, and then in the end they don't have the money for that, and then the mission is terminated. So I want to see those space agencies that have plans ahead really making these plans in available and a true vision. We need also to set some milestones together and make them available to all. And if you ask me about the 5 years from now, I think the blooming of the private sector in the space business, providing important data and products to customers in order to combat climate change issues, monitoring abundant and manned area under routinely manner is very important. And this will optimize the exploitation of Mother Earth and for the well-being life of all.
Thank you, Eyal. Henry, please.
Yeah, not a ton to add, I guess, but one addition from our perspective is, we talk a lot about improving our understanding of climate change with additional observations in science. I think what we often kind of forget to mention is that even if we stopped emitting carbon to the atmosphere tomorrow, we are still expecting probably decades of new reality of climate with very extreme and frequent weather events. And in order to save lives in our economies, we need to get much better adapting to this weather, and we need to do it faster than we ever adopted any kind of technology at a larger scale than we ever adopted any technology. So looking at the early warning systems and weather capabilities, hydrometeorological capabilities of most nations on the planet are decades behind where we need to be, and space and I think private-public partnership enable us to close these gaps, which have been actually growing over the last decades with few years of work, if we act together and we act wisely and decisively.
Thank you, Ray. As I learned today, and I actually already knew, it happens in our shift, and I'm glad to see that we are all committed to take action to mitigating climate change now and in the future as well. So we are finished for now. Please join me in thanking our panelists for this eye-opening conversation. And I would like to thank you for taking the time to talk to me in this space conference. Thank you.